In this video, we are continuing our discussion of curve fitting, and in particular, we are talking about linear regression. So given a set of data in the form xi, yi, where I goes from 1 to n, a linear model fit to this data has the form y of x is equal to ax plus b, where a and b are the model parameters. So if we have some data here with our linear model fit, the black dots here are the data of the form xi, yi, so x1, y1, x2, y2, up to xn, yn. The blue line here is the model of the form y is equal to ax plus b. Now at each value, we have yi is our measured data. Y of xi is the model prediction at that same x value. And then the difference between these two is our delta I. So delta I squared is the model prediction y of xi minus the actual data yi squared. So we can define S as the sum of all of those delta i's for all of our data points. So the sum of y of xi minus yi all squared gives us the sum of the squares of errors for between our model and our data. Now the model parameters, this a and b in our model, can be found by minimizing this sum of the squares of the differences, or S, between the data point and the model predictions. So if we have our delta i's defined for every data point, S is the sum of the delta i's squared. If we substitute our model form in, this S is equal to the sum of axi plus b minus yi. So this is our model prediction at xi, and then this is our actual data at xi, or at xi, which is yi. So all that squared and the sum of that, we want to make that a minimum by finding the values of a and b that would minimize that quantity. So to minimize S, we need to differentiate with respect to the unknown parameters a and b and set the two equations to 0. So partial S by partial a has the form shown here, and partial S by partial b has the form shown here. So we set both of these equations to 0. So this gives us two equations for our two unknown parameters, a and b. So we can rearrange and solve for a and b directly, which have the forms shown here. So they're dependent on these sums of the data points xi and yi, and n is the number of data points. So the model y of x is equal to ax plus b with these coefficients provides the best linear fit to the data. So it's important to talk about the coefficient of determination, which is also called the correlation coefficient. It is denoted r squared, or sometimes small r squared, and pronounced r squared. It is a number that provides a statistical measure of how well the model fits the data. So the value of r squared is calculated as shown here. So it's 1 minus the sum of the actual data minus the model prediction of the data. So this is our delta i's squared. And this is sometimes called the residual sum of squares, divided by the sum of the actual data minus 1 over n times the sum of the data points. And this is actually the average of all of the y values of all the data points. So it's the sum of that squared. So 1 minus the residual sum of squares divided by, this would be the total sum of squares. So r squared varies between 0 and 1. A value closer to 1 indicates the model is a good fit for the data, and a value closer to 0 indicates that the model does not fit the data. So again, looking at our expression here, we can consider the limiting values. So if this quantity, so the residual sum of squares, is equal to 0, then that means that r squared goes to 1, which means that the residual sum of squares is 0, indicates that the regression line is a perfect fit with the data. And at the other end, if our residual sum of squares is equal to our total sum of squares, then r squared goes to 0. And this means that the regression line is no better than a simple average, or y is linearly independent of x. So let's look at an example. We're given some data here in the form xi, yi, and we want to find the best linear fit to this data. So we can plot this and see what it looks like. Now, using a linear model, y equals ax plus b, we want to find the coefficients a and b that minimize the residual sum of squares with respect to the model, and we can also find the coefficient of determination r squared. So using our expressions for our coefficients, we can calculate a as this function of these sums. So if we just look back at the data, we can calculate the sum of xi, yi is 119.5. So that's this value here. N was 7. So that's this here. The sum of xi was 28. The sum of yi is 24. And then in the denominator, we have 7 times 140. So the 140 comes from the sum of xi squared minus the sum of xi squared. So the distinction between these is that here we're squaring all the values and then summing them. Here we're summing all the values and then squaring that result. So this is 0.839286. That is the value of a. And then using our expression for b, we can calculate b as the sum of y, which was 24. And then we plug in our a and multiply by the sum of xi, which was 28, and divide by n, which was 7. And we find that b is 0.071429, which means that our model has the form y is equal to 0.839286x plus 0.071429, so ax plus b. And then we can calculate the coefficient of determination, or the correlation coefficient, as using the expression for r squared. So we see that the residual sum of squares is 2.9911, and the total sum of squares is 22.7143. So r is equal to 1 minus this ratio, or 0.8683 in this case. So this is the, I have posted a Matlab script that performs these calculations, showing some of the intermediate values here, as well as the final model parameters and the final r squared value. So these are the data points with the linear model fit. We can also do this very easily using Excel. So this table puts together basically all of our quantities that we're interested in, all of our xi's, and then the sum, all of yi's, and then the sum, and all the other quantities that we are interested in. Calculates the a and the b as well as the r squared. And you are likely familiar with doing this using the trend line feature in Excel, where if you just plot the data in a scatter plot, and then you can go to add trend line and choose linear, it will provide the equation, which is the model, and you can see that the values for a and b are the same as what we obtained, and it also gives the r squared value on the chart.